Hello, and welcome to today's webinar on 5G infrastructure readiness. This will be the first in a series of webinars being offered by Intel and our partners to help drive digital transformation in the telecommunications industry. A few things before we begin. Today's session will be a mix of an on-demand recording followed by a live presentation from Intel's own Steve Palermo, and then concluding with a Q&A from Steve. Thank you, and I hope you enjoy.
Welcome everyone. Welcome to the 5G infrastructure readiness webinar. Good morning, good afternoon, good evening to everyone. In this 1 hour session, we are going to explore the 5G network related infrastructure and how we are getting ready to deploy 5G around the world. So today, my name is Nirav Dalal. I'll be the first presenter. I'm representing Award Solutions out of Dallas, Texas. And I also have my colleagues Godfrey Tan from F5 Networks and Steve Palermo from Intel. They will be also presenting after I present the overall 5G infrastructure. So in today's webinar, we are going to look at the 5G core network requirements first. What are some of the key goals of our 5G networks? After exploring that, we will look at the 5G end-to-end network and also focus more on the 5G core network. After understanding the key components of the core network, we'll look at what are some of the hardware requirements for that core network. After that, Godfrey from F5 will explore some of the applications that can be deployed on the 5G core network as well as the application servers. And then Steve from Intel will focus on the readiness of the 5G infrastructure. So here, the goal is we are going to first look at the performance requirements of 5G. As you probably are aware, we have deployed 4G LTE networks around the world, and now we are at the cusp of deploying 5G networks. The requirements are significantly high in terms of the user experience, in terms of latency, and so forth, so we will explore that, and that will result into the new types of 5G radio and core network. So we will look at the key building blocks of how we are deploying 5G network that will help us meet the performance requirements laid out by the industry. Once we explore that network architecture, we will look at some of the network functions as well as what's in the core network, what's in the radio network, and what could be at the edge of the radio network as well. We'll explore some of the hardware requirements related to the components that we are deploying both in the core as well as on the edge of the network. So here is a quick poll for you. We would like to understand a little bit of your interest. So what is your primary interest in the 5G core networks? Is that service-based architecture of the 5G core network? Is that the user and control plane separation? Is that virtualization, NFV, SDN that we talk about in 5G? Or is that user plane operations and traffic steering 5G? Please pick one of the answers. All right, what we are seeing is quite a few are looking at the user and control plane separation in 5G networks, also focusing as well on the virtualization, NFV, SDN, and so forth. Very good. Thank you all for participating in the poll. Let's now look at the first aspects, which is the core network requirements. So you may be aware that when we talk about 5G, we are exploring a variety of use cases. We talk about mobile broadband connectivity, we talk about fixed broadband connectivity, we talk about video sharing, we talk about augmented reality, we talk about self-driving cars, we talk about industrialized automation, we talk about connected vehicles, we talk about smart cities. There are so many use cases we talk about. Of course, we cannot forget voice services is the heart of the wireless networks as well. So what the industry has done is we have classified all of these use cases into possibly 3 different classes. One of the class is called Enhanced Mobile Broadband, or EMBB. In that Enhanced Mobile Broadband, as the name suggests, we focus more on the capacity as well as the peak data rate. We want to provide much better data rates as well as the user experience. At the same time, we want to offer these services to many devices simultaneously. What that results into extremely high capacity that is required in the network. The second use case that we focus on is called ultra reliable low latency communications, or URLLC. As the name suggests, it is focusing on extremely high reliability as well as very low latency. So when we think about the low latency, what are we talking about? Here, we already have the latencies in the order of 30 to 50 milliseconds in 4G networks. However, to support services like connected vehicles or remote surgeries or augmented reality, we need much lower latency. We are talking about close to about 10 milliseconds latency in the wireless networks. In addition to that, we also focus on the ultra reliability. What that means is the error rate should not be very high. We focus on the error rate of 1 in million bits per second, bits. So reliability becomes very critical as well. And lastly, the third use case is focusing on the massive machine type communication, or MMTC. This is where we focus on the IoT, Internet of Things devices. That will facilitate variety of different verticals, such as utility meters and so forth, connected cities or smart cities where there are so many devices on the streets which are all connected, as well as the pedestrians wearing various wearables, they are also connected. So when we think about these classifications, think about how much bandwidth would be required, how much capacity would be required in our 5G networks. Based on this classification, let's explore what kind of a performance goals we have to support these various types of use cases. So as you can see, we have 3 unique classes which are very vastly different. For example, EMBB focuses on very high data rate versus ultra-reliable low latency focuses more on the latency end-to-end as well as in the radio network, versus IoT type of devices focusing on the connection density. We have to densify our network so that we can support so many devices. So let's take one at a time. First, focus on the peak data rate. Here, if you think 10 years ago, when LTE was starting, our peak data requirement was about 300 megabits per second. 10 years later, when we are talking about 5G, now the data rate requirements in the downlink comes to 20 gigabits per second versus uplink is half of it, roughly about 10 gigabits per second. If you do the multiplication, here the data rate requirements are close to about 70 times higher than what we had in 4G LTE networks. The reason for this high data rate is not one application requires that kind of data rate, but if we provide instantaneous high data rate of close to about 20 gigabits per second, we can improve the user experience of not just one user, but several users who are in that cell coverage. Now let's look at the second part, which is focusing on that second use case of ultra-reliable low latency. In order to support augmented reality type of application, we are looking at the end-to-end latency of somewhere around 10 milliseconds. Now, you may wonder, how would we be able to achieve 10 millisecond type of a latency when today in our 4G LTE networks, the latency could be close to about 50 milliseconds. So first we have to start at looking at the latency in the radio network. So compared to LTE, which was about 10 milliseconds of latency in the radio network, now we are looking at less than 1 millisecond latency. You may wonder, how do we even achieve that kind of a latency? Now we have to do multiple things. Of course, the air interface of the 5G has to support different types of air interface or different types of slots to support this low 1 millisecond latency. In addition to that, we are going to change the network architecture of the radio network, as well as we are going to bring computing to the edge of the network, and we will explore what type of a processing would be required on the edge of the network. Lastly, the connection density. Here we are talking about supporting IoT type of use cases. Remember, we talked about massive machine type communication, or MMTC. This is where we are talking about supporting wearables, supporting utility meters, supporting traffic lights, supporting variety of video surveillance cameras and so forth. When we think about all of these, we are talking about the goal of close to, you can count the zeros, 1 million devices per square kilometer. Now, if you combine the high data rate as well as the high connection density, of course, every utility pole is not going to require that high data rate, but when you combine much better user experience of the high peak data rate as well as massive machine type communication, think about what kind of processing would be required, what kind of number of cell sites would be required in our 5G networks. Now, the last two aspects of the cell edge data rate and the overall cell capacity. When you think about that, we want to offer much better user experience no matter where users are. So our goal is to get to close to about 100 megabits per second on the cell edge of the 5G networks. That results into much better user experience for all the users. However, it also poses challenges, or maybe you can call it opportunities, in the 5G network to process the data very, very fast, as well as provide that processing maybe close to where the users are, so we can also reduce the latency for the users, in effect, improve the user experience. All of that maps to, you can see the cell capacity of about 10 megabits per second throughput per square meter. Now we are talking about extreme densification. As you probably know, 5G would be deployed in so-called millimeter wave type of a frequency, where the coverage would be very, very short, maybe 200 to 500 meters. Now we are talking about close to maybe 30 cells, where you would need only one cell at the frequency of about 700 megahertz. Or if you compare low band of 700 megahertz versus the mid bands that a lot of operators around the world are looking at to deploy 5G, if you look at the mid band of about 3.5 gigahertz, even there we are talking about close to about 3 to 4 cells to cover the same footprint of the 700 megahertz. What that means is we are looking at very high densification in our network to offer this type of performance goals. So in order to meet these performance goals, what are we doing in the network? What are some of the key building blocks that would help us get to this kind of performance goals? So here is a kind of our block diagram for various things that we are doing to improve the 5G networks. At the bottom is the new generation, next generation core. This is our new 5G core network, which is going to be extremely flexible, extremely modular to support various types of use cases. If you remember, our 4G LTE use case was maybe 1 or 2 use cases, like fast internet connectivity and voice over LTE. Now when we talk about 5G, we want very flexible, very modular, very scalable core networks. How is it possible? Now virtualization becomes a table stake. With virtualization, we bring in things like NFV or network function virtualization, as well as SDN or software defined networking. This network function virtualization allows us to separate the hardware from software. What that means is we can deploy cloud infrastructure in the core network. We can even bring the cloud infrastructure on the edge of the network and allow the software entity to reside on this so-called generic purpose cloud infrastructure. That allows us to scale on the demand as well as deploy this software entity wherever it's needed. In addition to that, we are also going to separate the control plane from the user plane. Now we talk about those things as part of the SDN. However, in the 4G network, the separation was not clear, and that's why deploying SDN was a little bit of a challenge. However, as we said, 5G network starts with understanding of separating this user plane and control plane. And you may be aware that as we get higher and higher data rate and high densification of our network, we would need lots and lots of processing on the user plane. By separating this control and user plane, now you can move the user plane closer to where the users are, in a way, on the edge of the service provider's network. Now, let's look at the network slicing. Network slicing, as the name suggests, we are kind of slicing our physical network. We are creating so-called logical networks out of maybe a single physical network. Here, the idea is sharing of our resources, because as you know, we have 3 very, very unique classification of the use cases we talked about earlier. The network cannot be completely optimized for all 3 of them. That's where logical separation becomes very important. And that's where 5G offers end-to-end network slicing. What that means is end-to-end quality of service that is required for a particular slice. That is possible only when you have deployed things like NFV and SDN in our network. Lastly, multi-access edge computing. This is where we are bringing so-called the computing of the cloud into the service provider's network. Not just the service provider's network, but on the edge of the network where the users are. If we bring the computing to the edge of the network, now we are able to provide much better user experience for the users for low latency type of application. We are still keeping all the communication between the user and the network very, very secure because this edge computing is still within the edge of the service provider's network. Of course, lastly, we cannot forget the new radio, and responsibility of the new radio is to offer much higher data rates as well as the low latency. And that's where we are going to introduce so-called the new radio interface in the 5G called 5G NR. Excellent. So now that we have seen all the key components of our 5G networks, here is a quick poll for you. In your opinion, what services are you most interested in? Here we have listed just 4 of those services. Is that the high data rate apps and the videos in 5G? Is that AR, VR, mixed reality, gaming, or is that IoT type of a connectivity for so many devices? Or is that value-added services? Please pick one, and I will give you about 15 seconds to answer. All right. I'm going to share the results very soon. Here, roughly about close to 50% of you are looking at providing high data rate applications and the video services. Maybe it may take a little while for your screen to refresh. So here you go. And almost half of you are also looking at the AR, VR, MR type of applications, so the low latency type of application. Excellent. I'm a little bit surprised that no one answered the IoT. Maybe it's an anomaly, but IoT would be also one of the key use cases going forward as we explore the number of IoT devices in the 5G networks. All right. So now let's go to the next topic, which is the 5G end-to-end network and the 5G core network. Typically, the 5G networks, when we look at end-to-end network, we typically divide that into 4 areas. The first area is, of course, the 5G devices. This is where the user devices come into picture. And of course, in addition to the smartphones and the tablets, now we are talking about so many types of devices, whether it's wearables, whether it's IoT type of devices, whether it's AR, VR type of glasses, and so forth. The second component of our 5G network would be considered called radio network, or the next generation radio network. Here, the key component of the radio networks are essentially, we call it G node B, or the next generation node B. The next component after the radio network will be called the core network, and this is where the 5G core network or the new core network would be deployed by the service providers, which will provide the connectivity for all the users to the intelligent cloud or to the data networks, whether be internet or whether be enterprise network and so forth. We have also introduced something called MAC, which is nothing but mobile edge computing or multi-access edge computing. And as you can see that we have put it close to the edge of the network or close to the radio network. And that's what is going to help us improve the latency for applications like AR, VR. Now, if we explore this network further a little bit, we are going to open up so-called the intelligent cloud into multiple networks. As we know, the 5G services can be offered by the service provider themselves. What that means is they are going to provide operator services such as IP Multimedia Subsystem or IMS. IMS is nothing but offering voice or SMS type of services. Operators can also provide value-added services such as content distribution or advertisement platform or location-based services. Or they can also connect with their partner networks to offer additional services such as entertainment. Finally, the core network will also connect us to the external services network. An external services network would be things like internet, things like enterprise networks, and so forth. Here, again, the idea is we are going to bring some of these services closer to where the users are so we can provide much better user experience. For example, some of the cloud services, we are going to bring it close to the radio network on the MAC server so that we can offer things like video compression, things like machine learning type of algorithms running close to the edge of the network. Now that we have seen all four components of the end-to-end 5G network, starting from device to the radio network, to the core network, and then finally to the services network, and then also bringing the edge computing in between the core network and the radio network, now let's explore the 5G networks in a little bit more detail. So what you see here on the left is our UE or the devices which are connected to the radio network through this 5G NR air interface. This is the new air interface. Through that, users are connecting to the radio network, which is nothing but essentially several G node Bs or the next generation node Bs, which are also connected with each other. What we bring in here is so-called a split architecture. What that means is the G node B would be split into two components, a G node B CU or the centralized unit. As the name suggests, centralized unit is going to be closer to the cloud or the network or the core network side of it, and the G node B DU or the distributed unit. As the name suggests, the G node B DU would be distributed and it would be close to, maybe you can just call it at the location of the radio unit or the antenna or the tower. The idea is to again reduce the latency, so some processing of the radio network would be done close to the antenna. Now you can think that where all we would need processing, not just the core network, not just the edge of the network, but even on the far edge of the service provider's network. On the right, you see the core network components, and of course, there are a bunch of acronyms. Don't get overwhelmed with that, but let me summarize some of the network functions that we see here. You can clearly see the separation of the signaling and the traffic, meaning the control plane and the traffic plane or the user plane. In the signaling, the AMF or access mobility function, this function is going to keep track of where the users are. It's going to keep track of the registered user and provide services. The SMF or session management function is the one that as the name suggests, is going to manage our sessions. What that means is it's going to provide the user plane, or it's going to manage the user plane where the UPF, the user plane function, can be located in the core network as we have shown, or if it is required to provide low latency application, SMF can deploy the user plane function or UPF close to the G node B. The separation of the user and control plane allows us to put that UPF in the core network or in the edge network. Finally, the AUSF or the authentication server function and the UDM or Unified Data Manager, they are the ones they are authenticating the users and providing security to our subscribers. Finally, the core network connects to the external packet data networks. Now, in addition to the basic 5G network, there are some complementary features also being added in the 5G network. You can call it the virtualization is becoming a table stake here. You can see all these network functions are all virtualized. So virtualization allows us to be agile and scalable and modular so that we are separating the infrastructure or the physical resources of our network separate from the software. Of course, as we require more bandwidth and we are supporting more users, it requires significant capacity. So the number of network functions that are deployed on the cloud infrastructure would be plentiful. Now you can also see that we are going to require significant amount of bandwidth, not just in the core network, but on the edge of the network, as well as something that connects, which is the backhaul network. Once we do the virtualization, network slicing becomes natural for our deployment. And that's how we are going to provide end-to-end quality of service to various use cases. And finally, the low latency type of applications is where we will need so-called MAC or multi-access computing. This is where we are going to bring some of the cloud applications or some of the core network applications like UPF to the edge of the network, also close to the radio network. So when you explore virtualization a little bit, it's not about just virtualizing the core network, but it is also virtualizing the radio network. So in this next slide, we will explore the component of the virtualized network in the 5G. So as you can see, mobile is talking to the G node Bs. Now G node B can be virtualized, or the RAN can be virtualized. You can think of the G node B CU, which is the centralized unit, similar to a baseband unit pool or BBU pool that can be completely virtualized. You may have heard this term vRAN. vRAN is nothing but virtualizing the radio network, especially the G node B CU. The G node B DU could be at the tower or close to the antenna, close to the radio unit. That may also be virtualized, and that's where we will call it far edge computing. Close to the BBU pool, you see the MAC servers, and that's nothing but bringing also cloud infrastructure close to the RAN. That's where we will be running the MAC type of application. Edge application, things like machine learning and so forth. On the core network, you see we have separated various layers. At the bottom, the hardware layer is where we will have the compute, storage, and networking. And of course, as we offer more users with much better user experience, we will need significant processing power both in the core network aspects of the cloud as well as on the edge network aspects of the cloud. on top of it, we'll be running both the control plane applications like AMF, SMF, as well as the user plane applications like UPF. Remember, we talked about the UPF, user plane function. This is very similar to what we have today in our 4G network called SGW and the PGW, or the serving gateway and packet gateway. Finally, that connects to the data network, external data network, through this N6 interface. And all of that need to be also managed end-to-end through orchestration. So now let's take a quick look at another poll. It will show up very quickly on your screen as well. This next poll is about which part of the 5G network has the highest hardware requirements. Let me repeat one more time. Which part of the 5G network has the highest hardware demand? Is that the 5G control plane? Is that 5G data plane? Is that operator services, whether it's operators or the value-added services, or it's the MAC? Let me give you about 15 seconds to answer, and then we will share the results with everybody. All right. What we see, you will probably be able to see the results very soon. What we see here is significant of you are looking at the high hardware requirements on the Mac platform. And I would probably agree with you. This is where the computation is going to go to the edge of the network, and that's where we are going to not only offer low latency but much better user experience while still being secure, because all of the connectivity would be going through the encryption, integrity protection, and so forth. So now let's take a look at my last component, which is the hardware requirement in our 5G networks. So as we looked at the 5G network, it has two key components that we will need to explore our hardware requirement. One component would be the core network, or the 5G core network. That's where the user plane function, UPF, equivalent of the SGW, PGW, will fit in. In addition to that, we are going to bring some of the cloud applications and the cloud content close to the edge of the network or onto the Mac server. So the computation will go on the Mac server, on the cloud platform, where we would be running various types of applications. If we explore some of these applications, the workload on the Mac could be a variety of workload, and my friends Godfrey from F5 will explore some of the workloads that they are looking at. But to name a few, of course, you will see things like load balancer, firewall, transport layer security, and so forth. That would require significant processing because we are still on the edge of the network. We need to process so many gigabits worth of user traffic in a very, very fast and secure manner. Equivalently, if you look at the workload on the core network, which would be so-called the 5G core network, and remember, the user plane of that 5G core network is essentially the UPF. That UPF connects with the data network through this N6 interface, and that's where we typically talk a little bit about the so-called GI LAN. That's where we will be doing a lot of things like deep packet inspection or video optimization and so forth. So here is one more poll question for you. In your opinion, what is the value of 5G and the operator services network? Are you looking at so-called low latency type of applications? Are you looking at the reduction in total cost of ownership? Are you looking at the applications that we are providing in a secured fashion? Or are you looking at, hey, because of the edge, we will have less data transported across the network? Please pick the ones that you think are most valuable. I'll give you about 10 seconds. And I will share the results here. Maybe I picked very quickly, but what I see here, your response is you're all agreeing on lower latency. That's one of the key areas that 5G operators are also looking at, providing the quality of services and exploring various types of use cases, whether it be connected vehicles, whether it's AR, VR gaming, whether it's remote surgeries. All of those applications can be explored with our 5G networks. So now I will hand it over to my friend Godfrey, and he will explore some of the applications that they are deploying in both 4G and 5G networks. Godfrey?
Oh, thank you, Nirav. Hello, everybody. This is Godfrey. I'm from F5 Networks, and I will now talk about some of the things that F5 is working towards in the transformation of the mobile infrastructure to one that incorporates the mobile edge compute. So currently, as you can see in this diagram, F5 VEs and VNFs are already deployed in the IT and the MSP space, and as well as the SP core. Here you see that in the IT and MSP space, F5 has already deployed, as you can see there, ADC, which is essentially load balancing, WAF, which is web application firewall, the FW, which is firewall, which is layer 3 and 4, the acceleration manager, TLS acceleration, which is essentially security, and layer 4 to layer 7 DDoS protection. In the SP core, we have TCP and video optimization already deployed and on GI LAN, the GI firewall, CGNet, deep packet inspection, DPI, traffic steering, DNS caching and security, and so on and so forth. So in this diagram here, you see that F5's VNFs are able to be migrated onto a Mac platform, which means to say that we do have the VNFs and the VEs and the tools to enable the migration from a centralized deployment in the data center or cloud to one that is distributed at the edge, or what you call the fog, in a Mac infrastructure. So on this slide here, here is a network slicing application that F5 has been part of the solution, where F5's GTP director and DNS director have been deployed, and these are load balancing traffic across a pool of S gateway and P gateways, eventually converging onto an F5 VNF, providing traffic detection function and traffic steering support function. And this piece of the solution where F5 is a VNF. In this next slide, you see here that both in the mobile edge and the mobile core, F5 Virtual Edition has been deployed. And in the case of the Virtual Edition that you see on the right, the big IP provides DNS caching, security, GI firewall, and carrier-grade NAT functions. So this would be in the GI LAN or the N6 interface. So this would be the N6 interface, since this is the UPF function, which is the the user plane function which connects to the data network. So to enable this transformation, F5 has a variety of tools that enable the migration of existing VEs and VNFs into a distributed architecture like a Mac platform. So these tools work very closely together. For instance, the F5's VNF manager provides lifecycle management, configuration management, auto-scaling, and auto-healing for F5's VNFs, which is to say that it can deploy as well as withdraw these VEs or VNFs from the infrastructure. Working together with it is BigIQ, which provides lifecycle management, application service lifecycle management, and auto-scaling. But it deals in the area of licensing these VEs and VNFs. Thus, once these VEs and VNFs are deployed by VNF Manager, the BigIQ will license them to activate them so that they perform their functions in the mobile edge compute platform. Together with these, we also have, F5 also has automation toolkits, for instance, cloud templates, declarative onboarding scripts, declarative application service, AS3, which is specially developed by F5, and as well as the ability for these VEs and VNFs to have a telemetry streaming to applications like Splunk to collect health and statistics of the performance of these VEs or VNFs in the mobile edge compute. So underpinning the F5's technology is Intel's QUICKASSIST technology, in which F5's VNFs have been optimized to work with the underlying chip technology from Intel to provide the kind of performance that a 5G network requires, as was described so eloquently by Nirav. So with a QUICKASSIST technology via SRIOV, security applications can have up to 5 times the transaction per second and as well as 2.5 times the bulk throughput improvement compared to a software-only architecture. This requires an add-on license. Major vendors right now support Intel's QUICKASSIST technology hardware in the form of Intel's PCH E62X chipset, as well as the QUICKASSIST PCIe adapters or the 8900s PCI adapters. The supported hypervisors today are KVM, and the BigIP version 14.1.03 is supported. And VMware will be planned, the support of VMware will be planned sometime on Q3 calendar year 2019. So here we have some performance figures that is been tested in the F5 labs. So for SSL performance without QUICKASSIST, we are seeing about 7.5 kTPS and 100% CPU utilization rate. However, with the QAT, QUICKASSIST, we are seeing 30 kTPS, but a reduction of CPU utilization. So here's the poll question for you. In your opinion, what do you think will be the initial applications deployed in the mobile edge compute platform? Please pick one. Oh, okay, that's interesting. I see the poll. Wow, almost all are equal. The video optimization, network slicing, and for applications for smart cities and transport industrial, and mobile edge compute breakout. Well, thank you very much for your answers. And I will now hand this segment over to Steve Palermo from Intel. Thank you.
Great. Thanks, Godfrey and Nirav. This is Steve Palermo from Intel. I am a live person, so hopefully you can hear me okay. I will be taking you guys through the final block of the webinar, reinforcing some of the points that Nirav and Godfrey made on the pre-recorded portion of the webinar. And in particular, I'm going to be basically bringing some of these concepts to light here with real solutions and real products, and hopefully pass along some learnings that we are experiencing here at Intel as we help our communication service providers and cloud service providers move toward 5G fixed and wireless infrastructures. And the first slide I have here is just to help us get our bearings of what network nodes we're talking about and where the applicability of some of our work is happening right now in real time. Like I said, with real products, real commercial solutions, and of course real end customers. So the two areas of most that are top of mind are not only the server edge or edge server, but also the core server, illustrated here within the red box. And really the key of what we're trying to do is figure out how best to balance and distribute the load for 5G services and, of course, 5G infrastructure, which has not been widely deployed yet. So a couple of key takeaways here on at least on the edge server side. As Nirav mentioned, higher subscriber density, lower latency, and then, of course, on the core server on the right, on the telco cloud and NFV platform, is typically the traditional core services and billing, and also support of new 5G mobile services. So what the trends that we're seeing is really an overcapacity. Better to have more capacity at the edge than less, as well as on the core side, at least for the first deployments of 5G. The real pain point there is communication service providers, do not want to have an initial or do not want to have issues with their first deployments of 5G. So overcapacity is a common thread, at least at the moment, until we tune and figure out how to orchestrate and distribute some of the newer 5G subscriber densities and mobile services. A couple of key points, or I should say key performance pillars, are number one, increasing throughput, and in particular security throughput for the IPsec termination points in the 5G infrastructure, while and at the same time simultaneously supporting an increased density of VNFs or virtual machines on the same server. You can't have one without the other, and the challenge here is to do both as we migrate from more 4G LTE to 5G subscriber densities, lower latencies, and more sophisticated 5G applications, as Nirav and Godfrey mentioned previously. And the way that we're doing that, at least right now, is a combination of workload-specific silicon, of course. This is our second generation Intel Xeon platforms. These actually started to ship in quantity as we speak right now, this week. And they were previously launched a couple weeks ago at our Intel Data Center Innovation Day. So I'll talk a little bit about the very first line. We call these second generation Intel Xeon Scalable processors and platform, or N processors for short, N being network or NFV processors. And we've coupled that with the help of F5 with our security acceleration product, which right now is either in an add-in card or or contained within the PCH. And we've been working with F5, as Godfrey mentioned, on the big IP product to actually optimize that solution. And when I say optimize the solution, it's really those two key performance vectors. Number one is increasing security throughput, while at the same time increasing VNF densities on the same edge servers and core servers. So let's take just a quick peek at the second generation Xeon Scalable platform, or processors, or N processors for short. This is the very first time Intel has released a workload optimized processor, especially for NFV and networking infrastructure. Again, these workloads are all pursuant to more sophisticated 5G apps, as well as increased density on the same edge server and core server. We've especially tuned and focused these processors for virtual switching applications, vector packet processing applications, and even security and other workloads that are that represent the top 5 workloads on some of the evolving edge servers and core servers. So this up to 1.3 to 1.6x is based on the top workloads running on NFV and 5G infrastructure servers today. And on the far right, you can see there's at least we have 3 options today: high, medium, and low. We take these, put them into the edge and core servers, and of course combine them with the security and compression acceleration that I show here as an add-in card called QUICKASSIST technology. And finally, merge that with commercial VNF vendors, big IP, F5's big IP being one of those lead applications. The reason why we picked F5 big IP, in fact, Intel didn't pick it, our end customers asked us to start with F5 and other security VNFs because of the capability to reclaim and liberate CPU cycles for higher density VNFs. The next slide here is represents some of the particular workloads on the 5G MEC and core that Nirav spoke of previously, just to get a sense of where acceleration technology as well as CPU technologies can help. So the little yellow boxes there are a variety of workloads that sit on the wire on the N6 services between the internet and the 5G infrastructure that we have made better through the use of our NSKUs as well as Intel QUICKASSIST. And the little graphic there on the far left shows the increase of about 2x in terms of TLS transaction as one real data point using the 6230N with QUICKASSIST and with our NSKUs. In addition to the increased throughput, we're getting upwards of 2x and even higher returns in terms of VNF density on the same edge servers and core servers. Kind of putting this together, and I realize looks like I am running a little bit over here, is just really a call to action here for those of you building network infrastructures, or at least gearing up to support network infrastructures in the next coming years, as early as actually as early as this year. Want to encourage you to reach out to some of the links that we have coming up here in this packet, which include F5 Networks, GI LAN, and Big IP product line that's enabled for both the shipping CPUs and then also QUICKASSIST technology in our latest server platform, and of course the F5 network VNFs, which have been enabled to leverage some of the hardware acceleration capabilities. So with that, and knowing that I'm running out of time here, I'll skip over the key takeaways and just jump right over to the learn, explore, and engage more. We have a couple of different white papers as well as some academy training, and of course reaching out to F5 directly as well as Intel representatives for more information. I know the last part here was a little bit rushed. I apologize for that, but it is what it is, and I am 2 minutes over. So with that, I'll go ahead and conclude at this time, and then hand it back to the moderator, and we'll also take a look at answering any key questions that may pop up even after the webinar. So thank you very much for your attention and dialing into today's webinar. And at this time, I'll hand it back over to the moderator. Steve back again here. I think we are having a technical disconnect here. I do not hear the moderator, so unless somebody speaks up, we'll probably go ahead and close for today. Again, thank you very much for attending this webinar.